And I'll share my screen. Okay, so what you need to do is just open a new browser tab and just type in Google Colab. And on your first Google search here, look for this link where it says colab.research.google.com. Go ahead and select that. And when you select it, you'll probably get a menu like you see on my screen. If you don't see this, and instead you see something that looks like this, what you can do is you can click on File and click on New Notebook. And this will open a brand new Google Colab notebook that looks a lot like a Jupyter notebook. There's only one caveat to this, though. You have to make sure that you have a Gmail account. Otherwise, it doesn't let you do all these actions. You have to sign in through Google. So if everyone has a Gmail account, then this should work without a problem. Okay, so did that work for everyone? Is everyone having any issues getting this running?
I'm in.
I'm good.
Yep, I'm good.
All right.
Yep, good here too.
Awesome. Okay. So what I'm going to do is I'm going to change this title where it says Untitled 16.ipymb. I'm just going to change the Untitled 16 to be Numpy Fundamentals I, because that's what we're going over. All right, so once you have that, let's go ahead and get started. So I'm just going to create like a little outline so you understand like what this workshop is going to entail. So the way I did that is I click on this plus text to open like a text cell, and usually it shows up on the bottom of your first cell. So I just clicked on this arrow that goes upwards to move it up here. So now when you have this as your first cell, we can use the markdown format in order to style our text. So in this case, let's say that just to make it simple, you put 3 hashtags, and let's call this as the title Numpy Fundamentals. So it looks something like this, and you can see the preview on the right side. And then let's see, actually let's make it a little bit larger. So let's do 2 hashtags.
Did you click text or code?
I click text.
Okay.
Yeah. And then within this text cell, just like in your first line, if you do 2 hashtags with Numpy Fundamentals, the following lines could be just like the different topics that we're going to discuss. So the first thing is how do we create like vectors in NumPy? We're going to talk about that. We're also going to talk about matrices in NumPy. And then we'll also go over some operations. So we're going to look at scalar operations, and we're also going to look at something called vectorized operations. So these 4 are very like fundamental to what NumPy is all about. But we are going to go over a few other things too, like for example, being able to generate random data using NumPy. And the other thing we're going to do is file input output with NumPy arrays. And besides this, I also have 2 challenges that I made for the group here. So I'm just going to put that as challenges for now, but I'm going to create a separate text cell which explains what those challenges are once we get to it. But for now, let's try to see if we can cover all of these topics before we get to the challenges. So this is just like the outline of what you would expect in this workshop. So let's go ahead and just run this text cell. So once you have it, it will look like this. So now we're going to start. So we're going to start with the vectors. So one of the cool things about this environment that we're using, Google Colab, is it already installs a lot of the popular data science / machine learning packages that are required for Python. And NumPy is included in that list. So the way that we can connect to the actual instance on the Google Cloud for this notebook is to click on this connect button that you see here. If you click on this connect button, it will say allocate and connecting. And once it initializes and it says connect, you'll see that you get 2 progress bars. one for RAM and one for the disk. If you highlight over it, you can see some specifics. So you can see that it's connected to the Python 3 Google Compute Engine backend. You can see that the RAM is 0.79 gigabytes out of 12.72 gigabytes, and you have disk storage as well out of 107 gigabytes. So it's really cool, right? That Google is literally allowing us to use random computing resources on their platform for free, right? We're not paying anything for Colab, so it's pretty convenient. All right, so now let's go ahead and get started. So as I mentioned before, NumPy is already installed within this environment. So all you have to do is just import it. So you can say import NumPy as MP, just like this. And the reason we're doing as MP is like this is called an alias in Python, where instead of just saying like NumPy over and over again, you can just say MP. It's like a short form of it, an abbreviation. So now if you go ahead and click this play button here, it will allow you to run this cell. And right now you don't see any output because all we did is we just imported the package. But since you didn't get any errors, that means that it is successfully working. That means you know it's installed and it actually ran. So let's say we create another code cell here. Let's go ahead and create our first vector. So I'm going to create a comment called vectors here. And I'm going to first create a list with the numbers 1 through 5. So I'm going to say like my list is just a list with 1, 2, 3, 4, and 5. So this is my starting list here. And then what I'm going to do is I'm going to convert this list into a NumPy vector. So the way we do that is through this data type that NumPy has called the mp.nd array. So the n-dimensional array is what allows you to create vectors and also multi-dimensional vectors or matrices within NumPy. So the way that we can set that up is by using this method called array from NumPy. So if we were to say mp.array, and then you just pass in your list as the argument to that, you will be able to see this list being converted into a NumPy array. So if you go ahead and run this, you'll see that you get this as your output. It'll say array with your list inside. Now, is this really that different from a list? Well, in order to figure that out, you could typecast what you just ran. So the type function in Python allows you to see what is the class or the data structure that we're looking at. So if you run this, you'll see that it tells you that it's a numpy.nd array. Whereas if you were to say, like, let's say, and use a print statement here and just say type my list. Let's say you were to do this, you would see that it says that it's a list, right? So this is how you can differentiate that these two things are indeed different structures. The first one actually is a list, and the second one is an array. Now, let's see if we can save this array as a variable. Let's go ahead and call it as here. I'll actually keep the type function. And over here, let's go ahead and call it as my VEC, short for vector. And all you have to do is just say mp.array and my list again. So this time we're saving the array as a variable called my VEC. So if you go ahead and run this, let's go ahead and create another code cell now. And let's just try looking at the type of my VEC just to ensure that it's actually a NumPy array. So we can see that it is. So now that's the case. We can now do some interesting things with these vectors. So the first thing that I want us to look at is how do you index them? So with Python, with lists in particular, you can index them pretty easily. So if you were to say like my list and you want to get the first element, you can just put a 0 inside these square brackets, and you would be able to get the first element, in this case, the number 1. So what if you were to do this with vectors? Well, luckily for us, the way that the array structure works is that it allows us to do the same thing. So if you were to say my VEC 0, you would see that you can also get the number 1. Similarly, like just like how you would with a list. So does that only stay true for single indices, or could it work for if you're trying to get a collection of indices? Well, it turns out that it works the same, and we can prove it. So if you say my list, and the way you do slicing in Python is you choose your starting index. So let's say we do number 1 as a start, put a colon, and let's say you put the number 5. The number 5 is actually not included. That index, the element corresponding to that index of 5 is not included, but everything before that, from your starting point to 1 minus this, that's what you're going to see. So if we were to look at this, you'll see you get the numbers 2, 3, 4, and 5. And now let's say you were to do this for the vector. You can say my VC 1 colon 5, and you'll see that you also get 2, 3, 4, and 5, except it just shows it as an array instead of just a list. So I want to show you that these operations are the same for the list and the vector. It's just the data structure that's holding this information. That's the only thing that's changing. But one of the cool things about vectors is that it's not that you're just limited to doing this simple indexing. Vectors have a lot of cool properties. So for example, what if you wanted to get some summary statistics on these vectors? Like let's say you want to get the mean of all these different numbers here. So let's say you do it for your original vector, which is my VEC. Let's say you want to get the mean. So the way you can do that is just say my VEC, and there's a nice method that you have when you do have an array. It's called .mean, just like this. And if you run it, you'll see that you get the mean. And let's say you want to get the standard deviation. You can also get that as well by just doing myvec.std. And you'll see that you get the square root of 2 here. What if you wanted the variance? So if you do myvec.var, you'll see that you get the number 2, right? Because basically it's just the standard deviation squared. So the square of square root of 2, right, is actually just 2. So it makes sense, right? We can verify that it's correct. And then the mean is showing as it should, right, from 1 through 5. So yeah. Okay. So now that we have the summary statistics here, we can already see a major vantage point that vectors have as opposed to a normal list. Because if you were to try something like this on a list, you would get an error, right? Because lists don't have these methods built into them. Instead, you would have to create custom functions which compute these different statistics and then pass the list into those functions as an argument to get the same thing. So this is a huge time saver, right? You're able to get some really valuable information with just a method as opposed to doing so much extra work. So that's a huge benefit to having a vector. Now, what else can we do with vectors? Well, one of the cool things about vectors is you can also look at what we call as the shape. So usually the way you would do that is by using the length function, or len, in Python. So if you were to do this for a list, you could see that it shows you as 5, right? Because you know there's 5 elements there. So technically, this does have a dimension of just having one dimension of 5. So we know that this list technically is a vector. So if you were to do like my VEC, you can do it in 2 ways. You could still use the length function. In fact, it would still work. You still get 5. But other than that, there's another thing we could do, which is called .shape. So if you say myvec.shape, just like this, you'll be able to get a tuple that looks like this. And in this tuple, the way to interpret it is this first number you see here, that would be like the number of elements in a single row, if you're looking at it as a vector. The other thing is after the comma, let's say you have another number that comes after that comma, then that would refer to the number of columns that you have. So right now we're working with vectors, so we know that there's only going to be one dimension that we're associating. But when we work with matrices, you'll start to see that there's two different numbers which this comma separates, where one refers to the number of rows, one refers to the number of columns. Now, another really interesting thing we can do with these vectors is, rather than just looking at it in this way, where you just have like 5 elements, we can also do something like this, where what if you wanted to switch it? So then it's like 5 numbers are showing as like let's say maybe a column. So let's say if you were to do like my vec.t, for example, this T means transpose. So you can transpose this structure. And if you do that, you'll see that right now it shows the same. The reason it shows the same is because technically you only just have 5 units. Like, we haven't really specified what is the row, what is the column. So before we can use this transpose, we have to do a little bit of a transformation. So you're also going to learn a really cool concept here called reshaping. So let's say you set my VEC to be equal to my VEC, and instead of using shape, we're going to use reshape. And in here, now you just have to specify, how do you want the shape to be? So in this case, let's say that our shape is just going to be the 5 comma, but this time you have 1 column. Let's say you would say in a tuple here, just put 5 comma 1, just like that. And if you do this, let's go ahead and take a look at the new shape of my VEC. So if you say my VEC dot shape, you'll see that it's 5 comma 1 now instead of 5 comma. So now that we have done this, let's go ahead and try doing the transpose of this newly reshaped vector. Now, if we see a transpose here, let's do the shape real quick. Let's see what's going on. So right now it's showing, okay, see, look at this. It did change. Do you see that? Instead of it being 5 comma 1, it's now 1 comma 5. And in this case, it does make sense that it would do that. The reason the output doesn't look different is because technically, what does 1 comma 5 mean? It means you have 1 row and 5 columns. So if you have one number corresponding to an element, which in this case, the element happens to be a column, then seeing it as a row would make perfect sense. Whereas in this case, when you're saying 5 comma 1, you're technically seeing the 5 elements. So let's say if you were to do my VEC, let's see what it looks like. Okay, so actually, no, this is how it should look, right? Because technically you have 1 column. So you're seeing that each of these numbers are now corresponding to a row. So we actually do see the difference. So if you were to do my VEC.t, there we go. See, now you can see the clear difference here. In this first one, you have 5 comma 1, because remember, the first number refers to the number of rows and the second number refers to the number of columns. So in this case, you actually do have 1 column and you do have 5 rows. Each number, which is separated by this comma here, you are seeing that it has its own list, and each of these lists are being represented as a row. So that's why if you have 5 of them, you would have 5 comma 1 as this shape. But then when you transpose it, these two things are switching. Now you're going to say that it's 1 comma 5. That means you have 1 row, but you have 5 columns. So that's why when you look at it, it looks just like a normal row vector, but it's really having a different shape than what you would expect. So that's really the difference between these two. So does anyone have any questions about that?
Yeah, just a quick one. If you can repeat that, what is the naming convention for the different parts? There's a vector, and what was the other one?
Yeah, so technically, like if we look at it in like the algebraic terms, there's really only 2 names. There's the vector and a matrix. But in this case, I guess we could add a little bit of additional terminology where your vectors could have like different shapes. So as you can see here, if we have one where it says like 5 comma 1, that means we have something called a column vector, where it has 1 column which represents the dimension, and you have a bunch of elements in that dimension along that axis. Whereas in this one here, when you transpose it from this column vector into what you're seeing here, This can be called as a row vector, where you're seeing everything in this direction horizontally, whereas with the column, it's vertical. But nonetheless, they're still both vectors at the end of the day. Does that answer your question?
Yes, that was perfect. Thank you.
Okay, awesome. All right. So does anyone else have any questions about this, or are we ready to move on? Okay. All right. Let's continue. So now that we have covered vectors, let's go ahead and take a look at matrices. So now we're really getting into something a little bit more interesting here, where besides representing data as just the vectors that you're seeing here, what if you had multiple columns and multiple rows? So that's what we're going to see with a matrix. So let's start with a really interesting example here, where let's create a new vector which has 6 different values in it. So let's say we call this as a new VEC, in which you just put the numbers, let's say 1 through 6. 1, 2, 3, 4, 5, 6, just like that. And in here, what we're going to do is we are going to transform this list into a vector. So we can do that just for saying new VEC is mp.array, pass in VEC is the argument there. And once you do that, then the next step is going to be, let's go ahead and reshape this. So if you say reshape, right now, and this is just a quick trivia question for you, what is the current shape of new VEC when you convert it into a vector using NumPy? There's 6 different elements, right? So what is the current shape right now?
It'll be 6 commas,
six
nothing.
Commas. 6
Yeah.
commas, that's correct. All right, so if you have 6 different elements, and let's say you want to turn this into a matrix, which basically is just another way of saying you want multiple rows and multiple columns. Let's say if you wanted to have 2 different rows, how many numbers would you expect to have in those 2 rows?
6 each?
True.
Well, right now you only have 6 in total,
Oh,
right?
okay. Yeah, you're right.
So how would you change that?
3. It'll be 3 rows, 3 numbers in each column.
3 numbers in each row, right?
Oh, yeah.
That's correct. So that means if you have 2 rows, basically the formula is you take the number of elements that you have and divide it by the number of rows. So just do 6 divided by 2, and that gives you 3, right? So that's how you would know that you have 3 numbers in each row. So the way you can change it so it actually displays it in that way is you can just say 2, 3, just like this. And now you would see that this original set of 6 is now going to be 2 rows with 3 numbers in each. So let's say you do that. Let's go ahead and take a look at our new VEC. As you can see, that's exactly what happened, right? You can see that in our first row, you have 1, 2, and 3, and in your second row, you have 4, 5, and 6. Now, sometimes what happens is this ordering of how the numbers are going to be put into these rows and columns, that might actually matter to some folks who are working on these interesting problems. So in order to specify like how you want those rows to be displaying, there's 2 different ways you can do it. One of them is called the C order, and the other one is called the F order. Basically, the C and the F order are just talking about 2 different programming languages. C is referring to the C language, and F is referring to, anyone know what F is referring to? It's a very old programming language, but does anyone know?
Is it like something Tran? Fortran?
Yes, Fortran, that's correct. So F is Fortran.
Thank you,
and then
Thank you, Medium.
Yeah. So yeah, that's correct. F is Fortran. So let's say you were to like look at the way it is right now. This would be the C order, where if you look at your numbers like one by one in the original sequence, when you turn it into multiple rows with multiple values in those rows, you'll see it still showing up linearly. Where if you want the first three numbers in your sequence to be in the first row, you're going to see that. And the next three numbers would be in your second row. So that's how C is going to order this. But now let's see what happens if you were to change the order to Fortran. Then what would happen? So let's say you try that. So the way you set it up is you put a comma inside reshape, and there's an argument called order. And you can set it equal to a string. So there's two different possibilities, C and F. So if you put F, now all of a sudden it's going to be Fortran. So if you go ahead and run this, you'll now see that there's a difference, right? You'll now see that if you look at the sequence, you're going to be able to see by looking at the columns instead of the rows, right? So instead of 1, 2, and 3, you're going to see 1, 3, and 5, and then the next one you're going to see 2, 4, and 6. So that's the way to understand the how the numbers are going to be sorted when you reshape it. There's two different ways, C and Fortran. Do you see the difference?
Mm-hmm.
Yes.
Okay. Awesome. So if everyone sees the difference, then that's wonderful. That really covers the reshaping. So now we all know that we have no longer just a vector. Now we actually have a matrix. And the way to know that is by looking at its shape, right? So you can say new vec.shape, and you can see that it's 2, 3. So that's how you know that you're dealing with a matrix. So now the next step at this point would be, what can we do with matrices? Well, one of the really cool things about matrices is that at the end of the day, the data type is still the same. So if you were to say type new VEC, you'll see that it's technically still a numpy.nd array. So in terms of what's available to you in a matrix, it's not that different from a vector in terms of numpy methods. So if you want to do the mean, you can still do the mean as if it were a vector. It would still work without a problem. Now, the difference, though, as to what you would get in a multidimensional vector, which you're seeing here, would be the way that you index it. So for example, what if we wanted to get this first row? So before with a vector, right, if you try to do a single index, it's going to just give you a single number. But when you have multiple dimensions, now it changes a little bit. So now let's say you were to say new VEC 0. What do you think you might get if I put this right now? What do you think would display?
Would it be the whole top array?
That is correct. It would be the first row in that array, right? You would see 1, 3, and 5. Yes, absolutely. So now what happens is that each index that you refer to in this way is now referring to a row. So now you might be wondering, can you also do the same thing with columns? And the answer is a resounding yes. So let me show you how you can do that. You can just say new VEC. And what you're going to do is you're going to assume that you're going to get everything from your first dimension, meaning the rows. So the way you can do that is just put a colon. And now what you're going to do is you're going to put a comma. And now all you need to do is specify the index of which row, which column do you want. So in this case, you have 3 columns, right? 1, 2, 3, 4, 5, 6. So let's say you want the one where it's like 1, 2. You can just put a 0. So now if you do this, you'll see that you get an array with 1, 2, referring to the first column here. So just to make it a little bit easier, I'll just say over here in a comment that this is a row index, and the one over here is a column index. All right. So are we limited to just getting like 1 row or 1 column? Actually not. We could get multiple ones. So let's say you wanted to get multiple rows. You could slice it just as if it were a list. So you could say, let's say you want the first 2 rows, right? You can just put :2 like this. And if you do that, you're going to get the first 2 rows, which happens to be the whole structure. So what if you wanted the first 2 columns? You can also do that as well. You can say new VEC, :comma, and now you specify your slice. So you can just put a :2 here, and this would give you the first 2 columns. All right, so do you all find that interesting? Like how you can manipulate rows and columns with an index?
Mm-hmm.
Absolutely.
All right. So now that you know how to manipulate that, let's say we wanted to reverse a row, where instead of saying 1, 3, and 5, what if it were 5, 3, and 1? So one way you can do that is like this. You just say new VEC. Now you just put 0 again. But this time what we're going to do is we're going to reverse this. So you're going to put another square bracket. And in this next square bracket, we're just going to put 2 colons and a -1. When you do this, basically the step is what is changing. The step of being -1 means it's going to look at it from the back, then to the front. So if you run it like this, now you get an array with 5, 3, and 1. Now, I know this syntax might seem a little confusing at first, but anyone have an idea as to why I put 2 sets of square brackets?
Is it this stop step thing?
Well, the step thing would help for the second one, but this whole concept of being able to put 2 like brackets to begin with, like why does that seem to work here? Any idea for that? So it might seem a little confusing at first, but let's try to break it down. Let's say if we were to say new VEC 0, just like this, what would you expect to get when you do that?
1.
Be careful. So I think it was Arshdeep who said it before. It was
You would you would expect to get the first element in the array.
Oh, yeah, the first element.
right. So in this case, the first element in the array would be the first
Row.
row. That's right. So if you do it like this, you're going to get an array with 1, 3, and 5. So if this is the output of your first index, what do you know about indexing arrays? So imagine if this were a variable. If this were a variable called first row, just as a simple example, and you know that first row is an array, how would you index this to get all the numbers backwards?
Decrement it?
Yeah, it's just like we did over here, right? With the 2 colons and a -1. So 2 colons and a -1. Now, when you do that, you're going to get 5, 3, and 1. So the reason we have 2 square brackets to begin with is because the result of the first index is actually another array. And from that array, you can then apply the indexing again to get another output. That's the reason why we have 2 pairs of indices. Does that make sense?
Yeah.
All right. Well, that's great. So now that we covered, just the basics of slicing and indexing with one-dimensional vectors and multi-dimensional vectors, which we can refer to as matrices. Now we are ready to go on to a concept called scalar operations. So now let's just review some basic math here that you might see in a linear algebra setting. So what we're going to do is I'm just going to create a text cell. And in this text cell, I'm going to put 3 hashtags, and I'm going to put the word scalars. So scalars are really, really simple things. They're just numbers, like numbers with no dimension associated with them. So let's say just like the number 1 or the number 2, or maybe 50, maybe 1,000, maybe square root of 4, right? All these things would be like examples of scalars. Because they're just digits, right? They're digits that you can multiply to other digits and do all kinds of stuff. So we refer to those dimensionless numbers as scalars. So the reason why we need to do that is, let's say that you had the task of, if you had like the numbers like 1 through 10, and someone were to ask you, could we multiply 4 to all of the elements from 1 through 10? So let's say you were to do that using normal Python. Using normal Python, you would probably have a list. So you can say like my nums happens to be, let's say, an empty list, and we're going to go through the numbers 1 through 10, right? So let's say you create like a for loop where you just say for I in, and let's use the range function, and let's go from 1 through 10. So you're going to put 1 comma 11 here, because the 11 is not included in the range. So it's going to start at 1, and it's going to go all the way to this number minus 1. So 1 and 10. So all the way. And then within this range, all you need to do is just change what your argument is going to be. So let's say you just say I is equal to 4 multiplied by the number. Then all we need to do at this point is just add this new I to the mynums. So you can say mynums.append I. And if you were to view mynums after you do this, you would see that you do get 4 multiplied to every single element in your list. Now, just for doing something just like multiplying 4 to 10 different numbers, we had to do quite a bit of effort, right? We had to create a loop. We had to go through a range of numbers. We had to reassign like each number to being 4 times that number. And then you have to add it to the end of a list. And then once all that is done, then all of a sudden you can run it. So that's a lot of work, right? Like for doing something so simple. But with NumPy, all of a sudden this problem disappears. All you need to do is create a NumPy array that has the numbers 1 through 10, and you can literally just do a simple arithmetic where you just say 4 asterisk and whatever that array is, and that's it. So let me show you that. So if you were to say scalar multiplication with a vector, let's say that you call it as the numvec is now an np.array. And just to quickly generate a list of 1 through 10, instead of just manually putting the numbers 1 through 10, you can use this function called list, which is going to convert whatever's inside of it into a list. So I'm going to put the range in here, and I'm just going to put that those 2 numbers, 1 comma 11. So this now gives you an array with the numbers 1 through 10. So if you say numvec, you'll see it gives you an array with the numbers 1 through 10. So now what I'm going to do is, in order to show you that concept where instead of going through this list and doing the for loop and all of that, you can literally just say 4 multiplied by this, just like that. And if you run it, check that out. It gives you exactly what we saw over here. Isn't that cool? So you don't have to use for loops to do these kinds of operations. You can literally just multiply them as if they're integers.
Some serious black magic there, Rishav.
Yeah.
It works. It works.
Yeah. Is it so it's just doing the same thing with less lines of code?
Well, it kind of is. In fact, if we really go behind the scenes, it's actually doing something a little bit different.
Or
Instead
it's
of
like doing whatever we're doing. Like it's basically us, yeah, doing whatever we're doing.
so the point is that it's actually not using. Yeah, well, actually, I don't know for sure if it's not using a loop, but when you get the output, it's actually not based solely on a loop. It's actually using that concept of a generator in Python. So then when you do cast it in this way, where you say 4 times numvec, it's going to actually cast out the entire array with the transformations. I think that's really what's going on behind the scenes, but I haven't looked into the source code for this concept for NumPy, so I'm not completely sure if they're not using a loop, but it's not like a traditional loop, because in this case, you're actually saving each transformation into memory and outputting it all at once. Whereas over here, it's a little bit different. Like you only get whatever you want to get from it as long as you ask for it. So it's not necessarily saving everything in memory, but it saves it when you request it. So that's really the difference between the two. So that's why this one's more memory efficient than this one. So that's why if you were to do this for, let's say, 10,000 numbers, this one would come out faster than this one. So that's one of the really cool benefits to doing it in this way. Now, are we limited to only multiplication in this case? Definitely not. Let's say you were to do this with division. So let's say you were to say numvec divided by 5, for example. You can see that it gives you an array of floats where each number has been divided by 5. So that's a really cool thing. Sometimes you might do operations with some of the summary stats. So what if you wanted to multiply the mean or subtract the mean from every single number in here, right? So you could just say numvec minus numvec.mean. And you'll see that it takes each number in the vector and it subtracts it by the mean. And what if you wanted to get the squared differences after doing that? Well, guess what? You can do that arithmetic as well. Just put a parenthesis around this and just double asterisk 2, and this will square it. So there's all kinds of things you can do. If you can do it using the order of operations, you can do it with scalars on vectors. So is that pretty cool?
Yeah.
Definitely.
All right. So now the next thing we can do besides the scalar operations is, what if you were dealing with multiple vectors at a time? So you can also deal with that using NumPy. So let's say you would say vector operations. So this means that instead of working with just a scalar and a vector, what if you had a vector and a vector? So let's say you had vec1, where it's an mp.array, and let's use that concept which we did here with the where you pass the list and the range. So let's say you were to do this for the list of the range from, let's say you start at 5, and we're going to end at 15. Well, not exactly 15. Actually, no, let's make it exactly 15. Let's do 16, just like that. And this would give you the numbers 5 through 15 in a vector. And let's say you have another one called vec2, which is basically 5 multiplied by vec1, just like that. So now that you have 2 different vectors, what if we wanted to just like manipulate them somehow? So let's say the first thing we want to do is, let's say, add 2 vectors together, right? So the way you can do that is, let's say, adding vectors. So you could say, let's say vec3 would be vec1 plus vec2. And let's say you actually call it out vec3. Check this out. You get 30, 36, all the way to 90. Technically, there are 10 numbers here, where the first one in the first vector is 5, And then the second one is 5 times 5. So 5 plus 25 is 30, right? So we know that it actually did that correctly. So what if you were to do something like subtracting vectors? So in this case, what if you were to do vec2 minus vec1? We should expect that the first number would be 25 minus 5. So you should get 20 as your first result here. So if we're to say vec4, you can see that indeed it does that. Like for each element, you can see that it's actually subtracting those elements. And you can do that with two different vectors. Now, there is a caveat to this, though, that they have to be of the same length. Otherwise, it doesn't work. So vec1 and vec2 both have 10 numbers. So that's why we could do this. And same is true with the addition. There's also another concept where what if you were to do something known as the dot product? So the dot product is really interesting. Basically, what that means is after you were trying to multiply elements in both the vectors, let's say in the first one, it's like 5 and 25. After you multiply the numbers in the corresponding elements, then the dot product says you should add all of those products together. So let's try to do it in two ways. I'll show you the first way where you actually do it using these operations. So let's say like this, where we will call it as the vec dot as a variable. And let's put a comment here that says that you're doing the dot product. So dot product version 1. And the vec dot is basically just, you take your two vectors, vec1, multiply it by vec2. And once you do this, let's say you were to surround this in a parentheses, because you want to preserve the order of operations. So if you do this first, this will give you the products. You'll get 10 different products, right? So 5 times 25, so 125, right? And then all these other numbers. But once you do that, then the dot product says that you have to add those products together. So one method that I left out from earlier is something called sum. So you can actually do dot sum on this. And when you do that, it will actually give you that final sum, which would, in this case, correspond to the dot product. So if you say vec dot, you'll see that you get 60/50 as an answer. So you can do some really intricate operations with just vectors as well as with scalars. So now what if we wanted to simplify this process here as to just a method? You can actually do that as well. So let's say I were to say vec.2 as a separate version. So we'll call this as version 1, or version 2, sorry. Dot product version 2. So in here, instead of doing what I just did, where you multiply them and then you add it up, you can also do something like this, where you can just say vec1, and the method is actually called dot. So you say dot, and then you pass in vec2 in here, just like that. So you apply it on a vector, and then you pass in another vector as the argument to dot. And once you do that, we can see that it does exactly what the first one does. So these are two different ways to get the dot product with vector operations in NumPy. But I like this one more because you actually got to learn conceptually what a dot product is. Whereas in this one, you're kind of just cheating. All right, so does anyone have any questions?
Sorry, I'm understanding the code, but what is a dot product exactly?
Yeah, so the dot product just saying is like, let's say you have like two different vectors where let's say that each one has like maybe 2 elements in it. So you maybe like the first one might be like 1, 2, and the other one might be like 3 and 4. So the idea is that at each corresponding index, so in this case, you only have 2 indices for both vectors. You multiply the numbers that are at each corresponding index. So as an example, let's actually sketch it out so you can visualize it. So it'll be a little bit better. All right, let's go over here. Oops. All right. Okay. So let's say, all right, in your first vector, we'll call it as v1. let's say it happens to just have two numbers in it, 1 and 2. And let's say that your second vector also has two numbers in it. Let's say 3 and 4. So the idea is that with the dot product, you can multiply these two vectors together and then add up the products. So basically what would happen is you would have 1 multiplied by 3, 2 multiplied by 4, and this would translate into 3 and 8. So at this point, the dot product says that we're just going to add these two numbers together. So then you end up getting 11 as an answer. So do you see how the dot product works now? Like we have this at the first index, this at the first index. Those two numbers get multiplied, and that gets stored over here. You do the same thing with each index going after that. So in index 2, you have 2 and 4. Multiply them together, store them here. Once you have all those things multiplied, then you just add those final numbers, and then you get this one single value at the end.
Yeah, thank you.
All right, you're welcome. All right, so now that you know how the dot product works, you saw two different ways that we can implement it. One of the ways without using the inbuilt function called dot, and then of course with the dot. So two very fun ways to use it. I wouldn't be surprised if this dot really just happens to be what we did here, because I mean, it would make sense, right? It's so easy to write. So it might be. But anyways, so now that we did that, right, for the dot product, and we saw how to do operations between two vectors, we saw how to do it with scalars and vectors. So you learned a lot already. Like you learned a lot about the different manipulations you can do with different kinds of data structures in NumPy. So now that you have seen all of that, and you also know about the summary stats, right? You know about the mean, you know about sum, you also know about standard deviation, variance. There are a couple other ones that are there, for example, like the median, but the median doesn't work with like a dot median. You would have to do np dot median, and then you pass the vector in there, and then it would give you the median. It's a very strange thing. Personally, I think they should fix that so you can just apply it directly. But what can we do? I mean, that's just how they've done it. So now that you know about those things, let's now go into two more concepts, and then we're going to do some challenges. I think we're actually on time, so that's wonderful. All right. So let's now go to this next concept, where instead of trying to like put in numbers ourselves, to create these arrays, what if you wanted to create random number arrays? So we're going to call this as generating data in the form of NumPy arrays. So here is a way that we can do that. In fact, NumPy is very extensible. NumPy actually has its own module called random. So it's np.random. And in here, it has a bunch of different methods that exist with it. So let's say as a starting point, you want to create a 2x5 matrix where you have random numbers that are in between 1 and 10. We can do that using something called randint. And in here, the way it works is the low refers to what could be the lowest number that you can have in this array. And then the high refers to basically just like how the range works, right? Where you specify like where you want it to end, but it doesn't include that number. So it's exclusive in this case. So let's say you were to do like 1 through 10, right? So your low should be 1, your high should be 11. So this would give you a boundary as to where your numbers could come from. Then the next thing that we can do in this case is you can specify what we call as the size. So right now the size says none. So what if you actually wanted to have a 2x5 matrix? So the way you can have the 2 by 5 matrix using this concept is you put in a tuple. The number of rows is 2, comma, number of columns is 5. So you can just do it like this. And if you go ahead and run it, you'll see that you get a 2 by 5 matrix with random integers between with 1 and 10 included in that range. Is that cool?
Just have an error running the code. I'm just looking one sec.
All right. All right. So while you're doing that, let me know once you get this running. And once you have it running, I have a little task for everyone. You can do this as an overall group here. And
Cool.
the idea is I want you to create a square matrix where you have 100 rows, 100 columns. And I want you to have the boundary of the numbers should be from negative 1,000 all the way to a positive 1,000. And once you do that, I want you to show me 2 different matrices when you do that. So what do I mean by the 2 different matrices? So actually, yeah, let's say if I were to leave it with just that, like from one matrix, how can you get 2 different matrices? I want you to think about that as you do it. So think about it as a group based on everything that you saw in this demo so far, how you might be able to do that. Take
Can you help
about,
me debug my screen
I'm sorry?
on this last thing? Could you help
Oh.
me debug this last thing?
Okay, yeah, sure. Go ahead and share your screen. All right, so basically what you have to do is, do you see how you have like a dot in between your parentheses there? And random, remove that dot. Yeah, now I think it should work. Yes.
Yeah,
All right.
okay.
All right. You're all set. Okay, so yeah, why don't the 3 of you take some time to figure out what I was saying? Do you want me to just write out that challenge again in the chat, just so you know what you have to do?
Okay. Yeah, that'd be great because I missed it as well.
Okay.
Yeah, yes, please.
All right, there you go. Take about 10 minutes to do that, and then we'll continue.
Oh, okay.
Also, feel free to like team up. It might be even easier if you work as a team.
So for the second half of the prompt there, you want us to create a second matrix from the first one without running randint again?
That's correct.
Okay.
Sounds tough, but I think you can do it. If you look back at the examples, you can see how we can do it.
Oh, without using what? Um,
All right, how's everyone doing? We doing good?
Yep, just working on the second part.
I just, yeah, same.
All right, in about 2 minutes or so, that's when I'm going to present my solution. All right, so shall I present how I did it?
Yes, please.
Okay, so I'm going to walk this through conceptually first, and then I'll show you the code. Okay, so let's go to the sketchpad here. So let's say that instead of showing it with the example with 100 by 100 for the concept, let's say you do it with, let's say, a 2 by 2. So let's say that when you generate your random matrix, let's say you get something like 3, 8, let's say 6, and maybe 5. You still have 4 different numbers in this matrix that are within some kind of boundary. So in this matrix that you have here, the idea was, how do you present this as 2 different matrices? So one of the ways that you can do that is, and this is addressing the second half of the question, right? So in the second half, the idea is that the matrices themselves are not actually different. It will have the same numbers, but the way that it's shown to you is different. So the easiest way to do that without affecting the dimensions would be change the way that they're sorted. Remember what we learned with the reshape, that you can change the order. You can do one with C and one with Fortran. So in this first one here, exactly the same, because technically it's already in C. So you can say 3, 8, 6, and 5. And in this one here, it would end up being 3, 8, 6, and 5. Technically, they're still the same matrix. It's just that the way that it's presented to you is different. That's the idea that I was trying to get you to do with the second half of the question. So how can we set that up with the exact challenge, right? So let's do that. So I'm going to go to the notebook here. And this challenge, we'll call this as challenge 1. So first we have to generate the matrix, right? So we're going to call it as, let's call it as challenge matrix or something. And it's just going to be mp.random.randint. You do -1000. And remember that the second number is not included. So if you want 1000 to be there, you should put 1001. And then for the shape, to make it 100 by 100, just put a tuple and just do 100, 100. And when you do this, you end up getting the matrix in the C order. So if you want it to be the second matrix, so you can call it as challenge matrix 2, you can just say challenge matrix dot reshape, keep the dimensions the same, but the order is now Fortran. So now if you were to look at each individual matrix, you'll see that they indeed, they look similar, but they're not, they don't, I mean, they're similar in the sense where it still has all the same numbers. But what changes is the fact that the position of the numbers is different. You got my point?
Yeah.
All right. So besides this second part here, how many of you got this first one?
I got the first one.
Hmm?
The second one, I forgot to put order F.
Mm-hmm.
And I just decided I'll just do, just change the shape. I did matrix 2 equals matrix 1 reshape. And then I did like 1000 by 10.
Oh, I
which
see.
is basically the same thing, but
Mm-hmm.
not.
Right. No, I see where you went with that. So technically that would still work as long as the rule says that the dimensions are allowed to be different.
Yeah.
Hmm. Another thing you could have done, besides using order F, is what if you took the first 50 rows and the last 50 rows and just switched them? You put the last 50 first and then the first 50 second. You could have also done that, right? Does that make sense? Like, you understand why that works, right?
Yeah. Because it's technically in a different order.
Yeah, it's technically in a different order, but you would still have 100 by 100 matrix.
Mm-hmm.
All right. So this is good. I'm glad that, I got a chance to give everyone a little bit of a challenge here. So now that we were able to take care of that, there are a couple of other ways that we could generate these matrices. So besides using random.randint, what if you wanted to have floating point numbers? So we can actually do that. So in here, let's say that the idea is generate floating point numbers within a range. So the difference is, instead of using randint, we're going to be using something called uniform. I say np.random.uniform. And in here, let's say you specify it similar to the randint, where you say negative 1000 and you say 1001. You can specify the size to also be 100 by 100. But when you look at the output, you can see that it's actually floating point numbers within that boundary. So that's the difference between that one and randint. The other thing that's possible is something called the linear space. So let's say that you have two different numbers, let's say -3 all the way to +3. What if you wanted to create values that are evenly spaced out between those two numbers? So let's say you wanted 10 numbers that are evenly spaced out between -3 and 3. So it should start at -3 and it should end at +3. So the way you can set that up is like this. So we'll call this as generating a linear space between two numbers. So you can say mp.linspace, and in here, you specify the start and the stop. So let's say that the starting one is -3, and the stop is +3. And where right now it says num equals 50, you can change that so that it's just 10. And if you do that, you'll see that it gives you 10 numbers in this array, but they're evenly spaced out. So it starts at -3 and ends at +3. So that's what the linspace does. Another possibility is, what if you want to draw random numbers from a probability distribution? So this is getting really deep into the statistics here. But NumPy actually has something called the standard normal curve, where you can draw numbers that are within that boundary. So the way that you do that is like generating from a standard normal curve, generating numbers. Is like this. You just say mp.random.randn. And in here, you just have to specify pretty much the dimensions. So if you were to do let's say 2 rows, 5 columns, just put 2, 5. And when you do that, you'll see that it gives you exactly that. So there's a lot of ways that you can generate numbers using NumPy. Oh, there's actually one more that I forgot to mention, which is generating arrays based on a range. So for example, you saw before, right, that when we did list and then you put range 10, and this gives you an actual list, right? But instead of doing something like this and then passing a NumPy array on top of this, you can actually do it all in one shot by using something called mp.arange. And within here, you can specify the start and the stop as if it's a range function. So let's say you do from 1 through 10, so just do 1, 11, and you'll see that it actually generates the array from 1 all the way to 10. So that's like a really nice shorthand way to solve it the way we were doing before. It's a nice to have. All right, so are you all pretty impressed with what NumPy gives you?
Impressed, yes.
Very.
Would you be able to define or give a definition for standard normal curve for me?
Yeah, sure. So basically, you can think of it like this, where let's say let's see what's the best way to do it. Right. Okay. So let me draw a sketch here. So whenever we talk about a normal curve, we're actually talking about a bell-shaped curve. This is my attempt at a bell-shaped curve. It's not perfect, but this is called a bell-shaped curve. And in this bell-shaped curve, the idea here is that you have some numbers in this axis. So usually whenever you have a normal curve, you can have it where it's concentrated at a mean, and then it also has like a standard deviation associated with it. And that's where you would find like where these tails would be. Now, in the case of a standard normal, it has two assumptions. The first thing is that the mean has to be 0. And the standard deviation has to be 1. That's really the difference between a standard normal and just a regular normal. The actual Greek name for these is actually called a Gaussian curve. So these are actually called Gaussian curves, where the standard deviation will, of course, stay the same, but the difference is where the mean would be, and based on that, the standard deviation would tell where its tails would be. So if you have like 3 standard deviations, like that's where all of the like the variation in this distribution would stop. Like it would be either 3 standard deviations above the mean or 3 standard deviations below the mean. So you can't really go past that. That's like where it stops.
Okay, makes sense.
Yeah.
Thank you.
So the idea is with the standard normal, it's actually going to be like this, where it's between -3 and 3. And the random numbers will be drawn in this space. Whereas with a non-standard normal, it could be a different mean, and the standard deviations you would have to manually compute so you can get the left and the right boundaries. So that's really the difference. All right.
Okay, thank you.
Yep, you're welcome. Okay. So now that we discussed that, and thanks for asking that, because it's really good to have some of that statistical knowledge. So now that we were able to figure that out, and you saw so many different ways to generate arrays, the last thing that we should discuss before we go to the challenges is going to be file input output. So with file input output, the idea is that you can save your arrays as files, and you can also load your arrays as files. So file input output. So in this case, let's just go with a very simple use case where, what if you wanted to save your array as a CSV file? So let's say you do this for your challenge array. All right, so when you go up here, what was it called? It was challenge matrix, right? Let's say you want to do this for the challenge matrix. So if you want to save your challenge matrix as a CSV file, you can actually do it like this, where you would just say mp.savetxt. And the way it works is you pass in the name of the file, and then you pass in your array. So let's say that the name of your file is going to be called challengematrix.csv. Then put a comma. Your next argument is going to be the actual array itself. So it's just going to be challenge matrix. The next thing, which is really important, is right now it's going to save it as a text file. But if you actually want it to be a real legitimate CSV, you need to create a delimiter. So the delimiter says, how will all the different numbers be separated? So in order to make it a true CSV file, which stands for comma separated values, you need to make the delimiter as a comma. So you're just going to say delimiter, and in a string, you're just going to put a comma, just like that. And when you go ahead and run this, right now you don't see any output. But if you do an ls in here, you'll see that you now have a file called challenge-matrix.csv. So let me know if everyone's able to get that. So everyone has that?
Yep, got it.
Nice.
Almost there. Is that LS or 1S?
ls. All right, we good?
Not working for me yet.
Okay. Abena, how about you?
Can you increase the size of your thing? I can't see the and then go down to the chat. Thank you.
All right, let me know whenever.
Richard, can you look at my?
Sorry, what were we saying?
Can you look at my screen for a minute? It seems like it's working, but there's also an error. But
Okay, and Abena, did you get it?
Yeah.
Okay, so let's go ahead and see your screen, Alex.
thanks.
All right, so let's see. Yeah, okay, so the problem is that after your challenge matrix.csv, you have a parenthesis after that. You just have to remove it.
Here?
Yeah, that one, remove that.
Oh, I see.
Yeah,
Thank
go
you.
ahead and try it now. Nice. And then if you look at your ls now, you should have it. Cool.
Oh, yeah. Okay.
All right,
you.
excellent. You're welcome. All right, so now that that's taken care of, now you might want to see that, okay, sure, you have a file that's generated, but what if you actually want to load it back into NumPy and see the matrix? Well, you can. So the way you can do it is like this. Create a variable, let's say challenge matrix new or something. And just instead of saying mp.save.txt, we're going to say mp.load.txt. And in here, you can see Colab is being very helpful to us and telling us what goes in here. So all you have to do is just specify the file name, which in this case is challenge-matrix.csv, and just specify the delimiter. So we're just going to say challenge-matrix.csv and make the delimiter as a comma. Now, when you run this, if you do challenge matrix new, you'll now see that you do end up getting your array as you saved it. Is that cool?
That's rather convenient.
Yeah.
Okay, wait, did everyone get that? Sorry, I didn't quite catch that properly.
Almost there. 1 sec.
Okay.
Mine still keeps saying challenge matrix is not defined when I put in np.savetxt.
Oh, maybe it's because like in your solution and my solution, when you did the challenge, maybe the variable name is different. So if you want to go back and see what you saved your variable as, you can just pass in that name for savetxt.
Okay.
Yeah, it works for me.
Awesome. And Arshdeep, did it work for you?
Yeah, it's working.
Nice. All right, so Abinand, you want to just quickly check that real quick, see if it works?
Yep, got it.
Nice. All right, so now that you saw how we can not only save arrays in files, but also load them back to see the actual array, you've successfully completed file input and output with NumPy as well. And there are some other formats that you can save files into besides the text. There's also something called the NPY, which is another extension. But in this case, it's not really that important to us because if you can save it as a file that everyone can interact with, then that's really all you actually need in order to make it useful. But of course, I do plan to add some more content to the NumPy series. So I will cover MPY files eventually, along with some other operations we can do, some more complex things with NumPy. But I think with everything you learned today, you can successfully play around with NumPy and do some pretty fascinating stuff with it. So that's one thing for sure. But in order to prove that, we're going to actually do two interesting challenges, which will involve all the concepts that you learned in this session. So this session is supposed to end at 3:30, so we do have quite a bit of time to work on these two challenges. So the first challenge is going to be related to what you did with the random data, but in this case, you have to generate what we call as a random polynomial. And what do I mean by a random polynomial? So let me go ahead and just show you an example in a sketchpad. So a polynomial is going to be something where you have some kind of input. You're going to have something that's multiplied to that input, and then it's raised to some kind of power. So maybe it's, let's say, like 3 or something. And you're going to just add some more terms to this. Let's say the next coefficient might be like maybe like 2. Then you have your input again. Then you might have a squared term here. And sometimes terms might not actually be there. But just to make it simple for the challenge, assume that all the different exponents will be there sequentially. From like, if it starts at 3, it will go all the way till there's none. So the next one might be like maybe like 4x. And the next one might be maybe just the number 1. So this right here is an example of a polynomial. And what your task is you have to generate what we call as a random polynomial. Your function should be able to generate these coefficients at random. It should be able to generate random inputs. And it should be able to map this polynomial to your inputs and give you the final set of results with your transform data set. So just to kind of give you an example of that, let's say that you had a 2x2 matrix where you have 1, 2, 3, and 4. You should be able to get 1 to the third power is 1, 1 times 3 is 3, 3 plus 2 plus 4 plus 5, right? So 5 plus 4 is 9, and then 10. So your first one would be 10. And then for 2, it would be 8 times 3, right? 24. And then you have 4 times 2, which is 8. So that would be 32. And then you add another 8, so that's 40. And then you have 1, so 41. And then so on for these two numbers as well. So that's how you would expect the output to be. This would be like your input. And you can also have another argument which tells you how many exponents will you have. So this would be your two inputs. and your output should be what you see here, based on whatever the random polynomial is that you generate. So to give you some hints as to how you can get started, I'm going to write out the challenge over here in a text cell. I'm going to call this as the random polynomial challenge. All right, so we'll say, actually, let's do 2 hashtags, and over here we'll put 3. We'll say instructions. All right, so must be a function contains 2 inputs, random number array and number of exponents. All right, and then the next thing I'm going to call as the hints. Use the number of exponents to design an array that contains random coefficients. And yeah, so let's do that and then say create an array of exponents, but reverse the order so the highest one comes first. All right, so this is your instructions and hints as to how you can build this. If you want some starter code to get started, maybe you can do it like this. You can say def random polynomial. And in here, I'll give you your 2 inputs. It's going to be x being your random number array and n being your number of coefficients. And in here, all I'm going to do is just say that you're going to return something, but it should be in this format. So this is how you can get started. All right, so if you really want to make this work within the time, you should team up. The 3 of you should, discuss, and I'll be here. I'll be listening to how you're thinking about this. And if you need help, I'll also help out. But I want you to give it a chance where the 3 of you are collaborating on this and trying to come up with this solution. So your time starts now.
Hi, everyone.
Yes.
Um,
I'm a bit lost on the math, honestly. This seminar shows to me that I need to brush up on my mathematics.
same. I think we should all of us just sit together one day and have a
Yeah,
maths.
exactly.
a
What
maths-
exactly
a
is it?
maths thing.
Yeah, I know you just explained it to us, but can we break down what exactly is a coefficient and what are we trying to put here?
So, for example, the coefficient is the number that is so I don't know, the number before the no, it's not the number, but is it the number for the x or the number that's like the exponent?
Is this the number associated with the variable?
Okay.
Yeah. So it'll be like 2x, 2 is the coefficient.
Okay.
Like 4x, it's x multiplied by 4. 4 is
Yeah,
the coefficient.
and 4 will be the coefficient.
Okay.
Yeah. So we need to create a random thing for n, right?
Yeah. So
So it'll be like
the way we did the random numbers, right? We're gonna
Yeah.
borrow that code, right? np.random.
yeah,
Randint,
np
and then
random.
.randint, right?
Yeah, and then we
And
generate the
which numbers we want to put in there.
yeah. And
Um,
then
Would it be, I guess we're defining the object here, right? So we have to,
yeah,
do you put it on the same line as define?
it has to be after. So we define random polynomial x, y, and then the next line would be x, I guess x equals. No, it
Or
won't
is
be.
it n
It'll
equals?
be yeah, and it'll be random dot rand in, and then the boundaries.
Rishabh, are we able to see the previous screen where you showed the matrices?
Yeah, sure. Do you want me to go up there?
Yeah, please, if you could.
All right, just let me know when I need to stop.
No, I'm sorry. The one where you showed the random polynomials example.
Oh, this.
Yeah,
Okay.
Oh yeah.
I'm just trying to understand what our input's going to be.
Hmm.
So yeah, we need to do the 3 here and the 2. Those are the coefficients. And then the x is the unknown, and then the 3 will be the exponent. So we're trying to just get the 3, the 2, and the 4, basically. That's the coefficient.
I'm just trying to the problems that we have random coefficients. Is that correct?
Sorry, can you say that again?
The problem said we had random coefficients.
Yes, that's correct.
Would that be different for each element in the input, or would that be constant for each of them?
Okay, so the idea is that when you have random coefficients, the number of coefficients should be based on how many terms you have. So in this case, the number of terms would be, let's say, if you consider n as like your highest exponent, then that means, let's say the highest exponent is like 5. Then one assumption that we're keeping in this function is that we're not including any like what do you call it, like any gaps between terms. So if you start at 5, then you know your next one is like 4, then you know your next one is 3, and then 2, and then 1. And the idea is that you're going to have one more than the number of exponents that you have, because as you saw over here, you have a +1. But what is this one actually, right? It's actually, you can consider it as a coefficient where it's 1 multiplied by x to the 0, because x to the 0 is actually 1. So that's how another way you can interpret it. So that means in total, you would have how many exponents? You would have 1, 2, 3, and 4, right? Instead of just 3. So if you have, sorry, go ahead.
Yeah, right. So the coefficient 1 and 4, for instance, did you say we randomize those, or are we going to use 4 and 1?
So the only things that are going to be random are the coefficients that are being multiplied to the terms, and also just this input itself. So if this input is like an array, or if this input happens to be like some kind of, maybe even a single number, then that would be something that's random. But really the only thing that actually gets randomized here is the coefficient, right? That's the main thing that gets randomized.
Right. I just need a clarification on that. Okay.
Mhm.
can use some help if you can.
She can leave in the car and get it because I'm the last few minutes. It's not practical.
So, Alex, Abena, how are we doing?
We have an idea.
I'm lost at what to return.
That's fine.
All right, so I'm gonna pick a random thing and let you guys just
Yeah.
shred me. So I'm gonna put it into the group content so we can at least propose something and then
All right. Would one of
we
you
can
like to
discuss
share
it.
your screen? We can also do it like that.
Yeah, I'll share my screen.
Yeah. Mm.
All right. So in this case, let's say that if n happens to be your number of exponents, then remember that, as I was describing to everyone, that the number of terms is actually just one more than the number of exponents. So if you have 5 as your highest exponent, you would have 6 different terms. So n plus 1 different terms. What you did after the return, where you did random.randin, and you created this set of inputs here, this would actually be maybe either your input. Yeah, actually, that's exactly what it would be. It would actually be like your input. So this would actually be the x, like what you did here.
Okay. So would I change that to this?
Yep, that's right. That works.
Then
So
have
now
to
what you
do
have to
something
do
again.
is you have to figure out what goes inside the function now. So to go inside the function, you want to start writing in here.
Okay.
So anyone have an idea on how we can get the coefficients?
I put in mine, what's your coefficient? X. No. We don't have to use a for loop. We can just do it, or can't we just generate it using random?
Since they're random, I just used np random.
Yep.
Yeah, just like np dot random dot randin.
Yep.
And then I put in like 100 minus 100 to 100, and then generated yeah, and then I did like 10 minus 10, 10. So it'll be, it'll generate 10 of them, for example. So in the parentheses, I made another parentheses which says 10. And then after that, I did another one for the
Sorry, guys, I'm back here. I missed last 90 seconds. Should someone else share their screen and I follow them, or I'm going to type?
All right. Well, since we're getting towards the end here, should I start writing?
Yeah, that's fine.
Yeah.
All right. So I'll show you some pieces. I'm not going to show the full solution, but just conceptually, just the way that I was, thinking about it is like, where if you know that n is like your highest exponent, then the number of terms you're going to have is n plus 1. So let's say that if you start off with that concept, let's say that you have chosen 4 as your n. That means you would have 5 different terms. So you have 5 different terms. Let's say just conceptually, it's just 1, 2, 3, 4, and 5, just for example's sake. And let's say that you're trying to generate random coefficients based on the number of terms that you have. So that means you create like a random.randint with a certain boundary in order to get random coefficients in which the shape has to match with the number of terms. So maybe you could have maybe like 20, maybe like 21, 40, maybe like 41 or 30. And when you do this, you now have a vector of coefficients, and you also have a vector of terms. Now, there's just only one caveat to this. Remember that the way that the polynomial starts is that the highest exponent should be coming first. So maybe one thing you might want to do to this is, could you actually reverse the order? So then the 5 comes first, and then the 1 comes last. So once you do that, this term is really supposed to be modeled after one thing, where it's really just the input raised to an exponent. And that exponent will be what you see here. So let's say if the first one is 5, then it'll be x to the 5th. And then the last one will be x to the 0. And once you have that, do you agree with me that this still has 6 and this has 6? And all you really need to do is just multiply the corresponding indices, and the answer would be just adding them together. So what's another way we could simplify that? Y'all remember the dot product? Using the dot product, you can take one of these. Let's say you do this on the coefficients. And inside the argument for the dot, you can just pass in the terms. They multiply up and they add up in order to get your final answer, which could be some scalar value. So that is ultimately how it works from an algorithm perspective. So how can we actually set this up? So let's actually write this out. So if we go in here in this random polynomial, let's say that you create a variable called terms. And you set terms to be n plus 1. So actually, instead of doing it like this, oh no, actually no, that's fine. Terms is fine. We'll call this as just terms. Just keep it as terms. It's just a number. This is n plus 1. And then what we're going to do is we're going to create the vector of exponents. So one of the easiest ways you can do this is just do an np.a range, right? So you can call it as exponents is an np.a range, and do this where it stops at terms. So you know it's going to go from 0 to 5, right? Because 6 is not included in this. If you were doing 5 as n. In this case, it would be whatever n is, it stops at n. It's not going to include n plus 1, but it stops at n. So now the idea is, remember what we said, we had to reverse it. So to reverse it, you can use your slicing technique where you just do double colon minus 1. And this will reverse it. So your first exponent is your highest exponent. So now what we're going to do is we're going to create the vector of random coefficients. So in here, let's say you call it as coefficients. You can just do mp.random.randint. And the boundary is completely up to you. Generally, I just do -1,000 to 1,000, 1,001, but it doesn't really matter. It could be whatever you want. Now, the important part here, though, is the size, right? The size is very important. So the size in this case is actually just going to be terms. That's important, right? It has to be the size of terms. So now that you have this, you now have an equal number of numbers in coefficients as you do with exponents. So all you have to do is create what you call as the term vector, which is you take the input, raise it to the exponents, and take that dot product with coefficients. So let's say you create the term vector. So the term vector would basically, you can just call it as a variable called term vector, where you just take x and you're essentially just raising it to exponents like this. And then over here, all we need to do is compute the dot product of the term vector and the random coefficients. So over here, you can just say dot, is this equal to coefficients dot term vector. And now that we've done this, all we need to do to complete this is just return the dot. So if this were just an example here, let's say you run it. Let's say you do random polynomial, and let's say you do this for a single number first, like let's say 3, and your n happens to be 5. As you can see, you do get a single scalar as the answer with just a single number. So what if you were to do random polynomial, and this time you do this with the numbers 1 through 10. So np.arange 1, 11, and just put, let's say 5 here. It'll generate another random polynomial where the coefficients are different, but the exponents will be the same, right? So if you do this, oops, a little issue here. So term vector saying x raised to the exponents. Okay. So this is where it gets a little bit trickier. So when you're trying to do this for more than one number, it's a little bit different, right? Because in this case, it's not as simple as just like raising one number to all the different exponents, right, to create a vector. Now you have like a vector and you're trying to raise that vector where the size is different from your other vector and trying to make it work. So you can't actually do that, right? Remember what we said before, that when you have vector and vector operations, that the vectors have to be of the same size. In this case, they're not, right? You can't operate 10 and 6 together. It should be 6 and 6. So when you have this situation, we have to do an adjustment. But for this exercise, what I want you to do is really focus on just a single number as the start. You just want to generate the random polynomial and be able to transform a single input into that. And that's what we achieved, right? We were able to do that. If you put in any random number, it would work. You would be able to get the answer. But if you want to be able to make it work for a lot of things, then here's a couple of ways we can do it. You want to know the easiest way we can do that? It would be just like this. All you have to do is just let's say that you're, okay, let's try to think about that. Because, okay, so think about it like this. There is a very easy way you can do it, but there's a drawback to the approach. The polynomial that it is using to transform is going to be different each time. But this is just like the fastest solution you can have for this case. where let's say that you have an array where let's say you call it X is mp.arange of 10 and or 111. Let's say you do this. Now what you would do is now that you have this thing, what if you were to now translate this random polynomial where basically each of those numbers is now going to be passed to the random polynomial. So one of the ways you can do it is maybe using a list, right? So let's say if you were to say, you can also, by the way, iterate through integers in an array using a loop. So if you were to say, like, for example, for I and X, you could do something like this, where you say random polynomial I, and then you keep it with the 5 exponents, or the 5 as the highest exponent. But there's an issue with this, right? The problem is that each time you're running this, you're drawing from a different polynomial, right? It's no longer from the same polynomial. But nonetheless, the concept still applies, that you're still able to transform a digit based on a random polynomial. But if you want the same consistent polynomial, then you have to do something a little bit different. What you would need to do is you would have to set it in such a way where you would be able to broadcast different sizes of vectors and of the terms and the coefficients. So the way that you would have to go around doing that would be in here, you would have to go through each of the elements of the X. And when you go through each of those elements, you need to make sure that you're multiplying the coefficient to that element raised to the exponent, and then you return those final outputs. I can show that to you if you want, but maybe to make it more interesting, what if that becomes your homework exercise? That sound like a plan?
Sounds like a plan.
Fun times.
All right. Well, I hope this was useful because you still got to learn some interesting stuff. As you can see, NumPy is very powerful, but it doesn't replace anything, right? Sometimes you will have situations where you won't always have the same number of elements with vectors or matrices. So if you do have situations like that, you still need for loops. But you can leverage what you learned from these vectors in order to expedite the process and make it more efficient by combining it with loops. So that's what I would say. But yeah, as you can see, like this solution here, this would work. Like you would be able to get like what you expect, but it would be from a different polynomial each time. So that's really the summary about this one. But if you want to do it for just a single number, you already have the solution for that. Changing it to work for multiple numbers is just a slight adjustment. All right. So I'm going to leave it here then. I think we're starting to go into the next session. So before we go to the next session, Arshdeep, I just wanted to quickly tell you about the premium subscription plans that I have going on for ChanR-Community. So as you might have seen in the workshops, that many of the workshops are priced at a certain dollar range. And some of them are more expensive than others. So I created a subscription plan that allows you to save money where you don't have to actually pay for all of those workshops, but instead you just pay like a monthly fee and you get access to all the workshops if you go for platinum, or for majority of the workshops with what we call is the gold subscription. So if you're interested in that, and I do cover a lot of different skills, like it's not just Python, you'll also learn about like Bash, developer operations, web development, more advanced data science, and SQL. And I also going over some other languages later on, like JavaScript, C++, Golang, Scala, a lot of like really in-demand languages that are out there. So if you're interested in that content, I can send you an Eventbrite link where you can subscribe either as a gold member or a platinum member, and I could automatically add you to whatever workshop you want to attend. So if that's of interest to you, then feel free to let me know and I'll be happy to add you.
Okay, I appreciate you letting me know.
Yeah. So do you want me to send you the Eventbrite link?
Sure.
All right, cool.
Is this the end of this current session?
So this is the end of this current session, and the next one is going to be on Bash programming. That one is a premium session. I think it's for gold members. But if you want, like I could, if you want to subscribe right now, I can add you to that, so you can join Jiro and Abena as a part of that.
Okay, I probably won't be able to make it today, but
Okay, so if you want to join like future workshops that are like premium, the easiest way to keep in touch with me is either through the meetup, or you can join the ChanR-Community Discord channel. So let me send you the link to that. So that way you can join this and get all the updates. So this is the link. I'm putting it in the Zoom chat. All right, there you go. That's the link. So feel free to join that, and then you know, keep in touch. And then of course, the next time a free workshop comes up, you know, you'll already be able to RSVP. But if you want to join the premium ones, you can contact me through this Discord, and then we can talk about getting you subscribed, so then you have access to all the other workshops.
okay, I appreciate it. Thank you so much for this session.
Absolutely, and thanks for joining. I hope this was a good first experience for you.
Definitely, definitely.
Fantastic. All right, Arshdeep, well, nice meeting you. So I'm going to start transitioning to the next call. So keep in touch, all right?
Okay, thank you. You guys have a good day.
All right, you too. Take care.